Okay, so before we just dive into what we have to do, the meeting is being recorded, and I would just ask for a minute. You guys prepare where to write. I'm muting myself. Once you do that, kindly just give a thumbs up. A pen and a paper. There are a few concepts that we might mention here and there which are not in here. So yeah, once you get, just give me a thumbs up. I will see it. Have we prepared? Okay, good. Uh, just give me a minute. Okay, good. So when we talk about locks, remember we talked about the issues to do with the transaction. Let's say there are two people here. We did talk about the reading and writing. Reading is just checking, writing is making changes. So if there are two people, they are just reading, we can't fall into any conflict. But the conflict comes in when one wants to read, one wants to write, or both wants to write. I think that's where the conflict comes in. So if one wants to read in the middle of writing, it becomes an issue because by then we looked at an example where there was an accountant and there was another person that was writing. So accountant wants to make changes, manager wants to check the balance. If the manager checks the balance before changes are made, that balance will be okay, or after the change is made, that balance will be okay. But in an event he checks meanwhile the changes are going on, that will bring about a dirty read. I think we did talk about that. So as long as one is writing or both are writing, it becomes an issue. Okay, so the observation, a reordering operation of the same elements around right causes different different program behavior. So what we are just saying here is, when you want to write, okay, when you want to write an operation, it makes that program to change its behavior. Remember, you are making changes. So in as much as we are making changes, we are saying it's either you withdraw or you deposit, and so on and so forth. So we talked about those conflicts that can occur, and we went on talking about two categories or groupings of conflict. There was intra transaction, so within the transaction itself. Then there is also inter transaction conflict. Okay, so there is a transaction A here, there is a transaction B here. These two transactions can can cause this transaction B can cause issue to transaction A, or vice versa. Okay, so in that regard, we are saying there is this transaction and this transaction. So we are saying there is transaction 1 and there is a transaction 2, and both of these want to write to X. Okay. Okay, so not always the same. Okay, uh, 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 transaction 1 and transaction 2 not always the same as transaction 2 and transaction 1. So the order, this is reordering that we are saying. So if we bring transaction 2 here, transaction 1 here is not the same as transaction 1 here, transaction 2 there. So remember, we have X here, we have X here. It means 1 wants to write to this X, 2 also wants to write to that X. Okay, so that will be a lost update. Videos will be available latest Monday. Yeah, I have been having a very big challenge around here in terms of network, but I think it is becoming stable. So that conflict can happen there. Also write conflict. So one is writing, one is reading. That can occur. So if this one writes, then that one checks. It's not always as remember, this is write read. Okay, so this is transaction 1, that's a transaction 2. The number tells you a transaction. So that's transaction 2, that transaction 1. It's not always the same. Okay. Then there's also read write. That's where we focus. We don't focus on read read. Read they are not making any changes, so it doesn't have effect. Okay, so read is not a conflict. So we dive into what we have to do. Scheduling. So scheduling or scheduling, if you like, there are these just terms that, if you like, English is not our first tongue, so some say scheduling, others say scheduling, and of course I agree with the people who call it schedule. That is a British way. Okay, so that is a scheduler, but you'd find in other areas they call that scheduling. So of course we've all attended meetings before, so you have a program to say, okay, I have a program at church, so I have to make sure that maybe I sleep in advance, I set an alarm so that I bath at this time. I would have eaten, then I start off. So you set a program, how your program is going to run. That's a schedule. So you have that as a schedule, which is quite important. In the same way, what we are saying is there are programs that are going to run concurrently. Concurrence means one after another. You have this program. Let's say I will. What's this now? Okay, check it later. Let's say you have a program going at the ShopRite. When you go to the ShopRite, you want to check on a price of certain commodities, and when you check now, you make the budget, and when you make the budget, you call back home. When you call back home, you ask for money according to that budget. When you have money, then you can get those commodities. So you can't check the prices at the ShopRite without going, and you can't make the budget before checking. You can't go home without making the budget. So you've seen those programs run after another. So program 2 depends on program 1. That sort of program running is called concurrency. Programs that run after another. Had you not gone to ShopRite, you wouldn't have checked for prices. Okay, so as long as the going doesn't happen, the checking can't happen. Now look at this. The result of you going to ShopRite will cause checking. That means the program of checking will never happen unless you went. Give me a minute. Just give me a minute. Just to respond to this. Of course, in a message. Okay. So, just like in the bathroom, whether I use a bathroom, you use a shower, that's not the topic of discussion. Going into a bathroom, if you don't go to the bathroom, you don't go to the shower, you won't bath. That means the issue of bathing will never start unless you go. That's what we are saying. So as long as you don't go, that will not start. In the same way, if you don't wash your hands, the eating of shima won't start. So the result of an activity 1 is the input to an activity number 2. As long as the activity number 1 doesn't happen, the activity number 2 won't happen. Or activity number 1 begin, but it doesn't finish. You move from the campus, you start going. No sooner okay, we don't have to go into that English. So as soon as you leave that Unza tunnel, you meet your friend. When you meet your friend, a friend say, escort me into town. The journey started, but that journey diverts. So the checking of prices at the ShopRite keeps on waiting. So activity number 1 has to finish, to start and finish. Then activity 2 begin. That's concurrency. So as long as activity number 1 doesn't start, or it starts then doesn't finish, then activity number 2 won't happen. So when activity number 1 starts and finish, activity number 2 depends on activity number 1. So number 2 starts, begins and finishes. Activity number 3 begins and finishes. So these activities run one after another. That is concurrency. Now, that concurrency, there is a software called scheduler. So a scheduler now put a program to those activities. So a scheduler is a concurrence control manager. I think we've tried explaining that, unless you have a question on that. Otherwise, you can give me a thumbs up so that we make the progress. Is that understood? Is that understood? Do we have people? Only one? Only one? Phrase, Fafa, is that understood? Is that understood? Otherwise, ask a question. Okay, phrase is fine. Are you in the meeting? We don't know for sure. Okay. Okay, so we have concepts such as pessimistic and optimistic concurrence control. Okay, so of course these terms, we use them in everyday life. So pessimistic and optimistic. So pessimistic, they are pessimistic people and there are optimistic people. Pessimistic people do not have a doubt. We are saying everything will happen. So there will be no issue in that. Optimistic, we are saying, okay, if there is a possibility of uh, um, of an activity going wrong, what are we going to do about that? So optimistic people prepares for whatever comes. Pessimistic, we're just saying everything goes as planned. Okay, so in pessimistic concurrent control, we assume the possibility of the conflict or probability of the conflict to occur as the higher chance. Just give me a minute. Just give me a minute. So sorry. We should correct that. We have swapped the explanation of those. Pessimistic, we are looking at the possibility of an error to occur. Optimistic, we are looking at the possibility of an error not to occur. Please pardon me for that. So pessimistic, we are saying if there is a chance of an error to occur, we have to prepare for that. Optimistic, we're just saying let us do this. Like what happened in campus. Instead of testing, they went ahead and buried. Okay, then after testing, they started that again. So in pessimistic concurrence control, we assume the possibility of conflict or the probability of conflicts to occur. So there are higher chances. So for this reason, we need to find a way of managing conflict. That is, if it occurs, or preventing a conflict from occurring. Optimistic, in optimistic concurrence control, we assume the chances of conflicts to occur is basically 0. So that is optimistic. Okay? And everything is optimal. Okay, so there is optimistic scheduler. We are saying it is often interchangeable with multi-version concurrence control. Okay, so the main idea of optimistic is execute first, then check later. It has cheap overhead. Okay, overhead is a delay. Then it is very expensive to abort. Okay, pessimistic now. Do we have another one? Okay, so pessimistic now, we are saying it is commonly interchangeable with locking. So this is what we will focus in. So when we talk about pessimistic, we are talking about locking, and this is the topic of our discussion. So we are saying we may end up in a locking situation. You have activity A, you have activity B, what you are saying is activity S begins as long as it doesn't finish, activity B won't happen. So you go in your bathroom, you begin showering, then other people are waiting. In the shower, because it is cold, you collapse. Then other people keep on waiting. Those people will keep on waiting indefinitely. Okay, so you are in a locking situation. Those people are stuck. They can't do anything about that. Okay, you go in the bathroom, you lock yourself meanwhile bathing, other people begin waiting. Funny enough, you've locked yourself in there. Suddenly you can't find where you've put the key. Or someone locks you from outside. You are stuck. You are in a locking situation. That is pessimistic. So if that was to happen, you assume the worst case scenario. What mechanisms are in place so that if that happens, how would you solve the issue? So the assumption is the execution of a transaction will result into conflict. What is the main idea? Okay, you have to prevent the execution that will cause conflict. That's the main idea. Okay, what is the advantage of pessimistic? It is cheap to abort, but very expensive overhead. In terms of delay, it brings about a lot of delay. Question: what mechanism do you use to make conflict serializable schedule? I think we've talked about conflict serializable. Last time we discussed that when a serializable schedule can be taken back to a serial schedule by the means of interchanging non-overlapping transactions. That schedule is conflict serializable. Please, the videos will be available, but I've shared the notes. Okay, so what mechanism do we use? The mechanism is called 2PL. That is two-phase locking. How are you going to get out? Okay, or here is the bathroom. You don't want the neighbors to be using, so you begin locking. Now, once that key go missing, what are you going to do? You need to have a spare key. That is two-phase. Okay, there is also timestamp ordering protocol. Also wait die. We will dive into those. Timestamping will be a topic on its own. Okay, locks. Pessimistic CC means concurrence control involves locks. So there are types of locks. Number one is called binary lock mechanism. So we only have two locks, that is in binary. Okay, and in this we use what we call precedence graph rule. before anything, okay, wish I can display that. Let me look for that. Can I find it so that I show you? Okay, good. Okay, I hope you remember this. We said we'll look at it in a good way. I hope you remember this. Do you remember this? Do we remember it? Kindly give me a thumbs up. Do we remember that? Okay, good. So now we do this. And that's where we are going. Okay, so we have binary logs and we use what we call precedence graph. Okay, please take note of this, because you find questions even in our exam before us, they will ask you to use the precedence graph. So you need to know what a precedence graph is. So a precedence graph is just a graph which is used to determine whether a schedule is conflict serializable or not a conflict serializable. That's a precedence graph. Know it by definition. So we draw an arrow from A to B. That is a rule. We draw an arrow from A to B if and only if A, there is a read operation on transaction 1 and followed by a write operation in transaction 2 on the same field. A commit is a commit. We'll talk about what a commit is later. So let's see what this is. Remember, read is not a conflict. So you skip read. It is only write, read, or read, write. Remember that. So we are taking time so that you don't say, no, this is what is happening. So what we are saying is this. You only draw an arrow, okay, from A to B. So this part is part A, this part is part B, if and only if one side is a read, one side is a write. One side is a read, one side is a write. And this read happens on transaction 1. There is a transaction. Then this write happens on transaction 2. And this transaction 1 is different from transaction 2. Then the field is the same. What is in the bracket is the same. Read on 1. A is the field. Then write on 2. Not write on 1. If it is 1 and 1, that is the same transaction. And we'll look at what that means. Number 2, when there is a write operation. So what we are saying is there is this write operation. So when there is a write operation in transaction 1 followed by a read operation in transaction 2. So there is a write there. Okay. This is 2. It doesn't matter which one starts. So what we are saying is if 2 starts, then there's a read here. You have a arrow. So this can be 2, this can be 1. This can be 1, this can be 2. So what we just did is switching this, getting it there, then switching this, getting it there. These are the situation you draw arrows. Okay? Number 3. Okay? If there is a write operation on a transaction 1 followed by a write operation on transaction 2. So there is this write here and this write here. This is on 2, but the same field, what is in the bracket is the same. A read and a read does not matter because it's not a conflict, so ignore that. Example. So let me take you back. So this may look confusing. This may look confusing because there are all these arrows, there are all these arrows, there are all these arrows, and all that may look confusing. But what we are basically just saying is this. Okay? So what we are saying is the following. So there is this here. That is almost the same. I was just drawing the arrows there. So you have 1 here, you have 2 here, you have 1 here, you have 1 there, you have 2 there, you have 2 there. So the best is you have to draw a table. And this table needs to have those numbers. So you have only of 1 and 2, 1 and 2, 2 and 2. So you only have 2 numbers, 1 and 2. So you put transaction 1, transaction 2. So these numbers represent transaction. Okay? Then you divide that in the middle. So let's do this. When you divide this in the middle, you put the reads and the write in their respective transactions. So R is in 1, so you start right from the left. R is in 1, so you have R, the field there is X. R is in 2, okay? So time increases going down, so you don't put in the same row. So this Rx, which is R2, because it is in transaction 2, will come below that. So the time keeps going like that. Then there is the write 1, so you have the write 1 X there, which is this in 1, so WX, you put it there. Then you have RY, because the transaction 1 happening there. W2, W2. I don't know if that should be 1. So W2x, which is WX into W1x, and so on and so forth. I don't know whether I did even this right. Okay, nonetheless, let us communicate a point here. So, you begin checking. You only draw an arrow from T1 to T2 or T2 to T1 if and only if this is a read and this is a write, or this is a read, this is a write, or this is a write and this is a write. Very important. So what you do here is as follows. You all have 2 transactions. So transaction 1 and transaction 2, you begin checking. Time keeps increasing. Please take care, take note of this. Time keeps increasing. So you have in transaction 1 a read. You have in transaction 2 a read. So you don't draw an arrow like that. So you draw an arrow from the guy on top to the bottom. You don't do the guy on bottom to the top. So you don't do this, then you do that. Because this, if this was 4 minutes, this here will be 5 minutes. So you can't go back to 4 minutes. You can only go to 6 minutes, 8 minutes, and so on and so forth. So here now, you have a read in transaction 2. So transaction 2 is here. It's a read X. Go the other side. Below this, on the other side. Not in the same transaction. In the same transaction, do not draw. Okay? This is the same transaction here. It's either from transaction 1 to transaction 2 or transaction 2 to transaction 1. So, you read X. Here you are writing X. So from T2 to T1, you draw an arrow like that. An arrow like that. Okay? Then, this same read, check what is below is read. So, read and read no. This read no. So this is done. You come back to this. This is a write. Don't go on top. Time has already passed there. You are here. So this is write. You are writing on X. What do you have here? Write. You are writing on X. Same field. So you draw an arrow from transaction 2 to transaction 1, which is that. Now, since there is this, the first one went there, the second one went there, so there is this circling. Okay, so what we are saying is transaction number 2 depends on transaction number 1, because transaction number 1 is pointing to transaction number 2. It means transaction number 2 wants some results from transaction number 1. At the same time, transaction number 2 is pointing back to transaction 1. It means transaction 1 wants the result from transaction 2. So you would find that these will keep on waiting indefinitely. This transaction number 2 says, I want the results from you. Transaction number 1 also says, I want the results from you. So this shows a graph. So when there's a graph like that, we are saying this is not a conflict serializable because of a cycle. It is not a conflict serializable because of a cycle. And this graph is what we are calling precedence graph is a graph used to determine or to show whether a schedule is a conflict serializable or not conflict serializable. Let me pause here. Are we good? Okay, Dan is good. Professor is good. Fanny, are we in the meeting? We're getting worried because you're not even responding. Are you in the meeting, Fanny?
Yes, I am.
But you're not responding. Is that understood?
Yes, it is.
Okay, good. So please take note of that. So you're gonna have something like this: transaction 1, transaction 2, transaction 3. Supposing they are there, then you start. So this is a read, whatever is on top. Okay, let's do this. Okay, so this is a read, not in the same. You go to 2. What is here is a read. So a read and a read doesn't matter. You go to 3. Remember, time increases going down. This is a read. Doesn't matter. The same guy, you compare it with that read. It doesn't matter. But you have a write here. Okay? So the first guy here, on A, you check the entire column. You have write on A. So you have an arrow from T1 to T2 because you are writing on A. Then you check the first one against this column. You check. This is read, this is read, this is write, this write is on B. So you can't draw an arrow from 1 to 3 because the field here is B, is A, the field here there is B. You move on. R in B, basically read on B, write here we are write on C, write on A, so that is not the case. Then you come here, read on B, write on B, so you have an arrow from T1 to T3 and so on and so forth. Then you've done away with that one. You come here because this is what you have. You check this against this because this is below that. So read A, read C, this is write B. So you don't have an arrow from T2 to T1. Then you check this against that. This is AC, read, B there. You don't have an arrow from T2 to T1. You are done there. You remain with this. Write B. Don't compare much to that. This write is above those two. So time has already passed at this point. So don't worry about the commit. We're gonna talk about that at a later stage. So you write B there, okay? You check here, do you have write B or read B? No. Do you have B? Yes. So you have from 1, 2, 3, and the like. Okay. So if you do that, you're gonna end up with something like that. So T1, T2, T3. Then wherever you have, you put arrow. So this is a conflict serializable. Why? You can see from T1 to T2 you don't have a graph like that pointing back and forth. You won't have this, you don't have back. You won't have this, you don't have back. So each arrow is just on a single direction. That is why it is conflict serializable. Okay, can I find out, is that concept clear? Is that concept clear? Perseus, it's clear. Danny, Fanny, is that concept clear? Because I will give you a question to work on just after this, so you better get it. So, binary lock mechanism. So we have locks on objects that or which specify which transaction can do the operation. So here we're just saying we have to choose which transaction can do the operation. So a transaction must acquire a lock before reading or writing. The notation here, okay. So the notation we use is this: X arrow LI X, which means the transaction I. Okay, this I here is a transaction. So a transaction I acquires a lock on element. So this transaction I acquires a lock. L is a lock. A transaction I acquires a lock on this X, which is that X. So the moment it acquires a lock, no other transaction will be allowed to perform. Okay? So a transaction must eventually release a lock. So we use U for unlocking. What it means is this transaction I releases, which is unlocking, that lock on a field it acquired that lock. Okay, are we good? Are we good? Give me a thumbs up. Are we good? Fine. 5 minutes break. We drink some water. Pero mereka bantu, bantu 50. Nggak pikir begini. One, two, 50. Whatever I was saying wasn't being recorded. I don't know, because I was trying to make some calculations. I hope you guys didn't hear anything. Forgot my mic wasn't mute. Did we hear anything? Danny, did we hear anything? Any of what I said? Fafa? Nope. Okay. That's a good one. Okay, that's a good one. Okay, so just for a few minutes, Perfius. Did you hear anything, Perfius? Did you hear any of what I said? You're laughing at me. You're laughing at me. Okay, okay, yeah. Okay, so that is what we that's what we're saying. So we'll send you a question, and that question will be dropped in the group. Please make an attempt. Granularity, okay. So the database management system and sometimes the users themselves may specify what granularity elements are locked. Granules. Granularity comes from the term granule. So a granule is just small. Okay. Let me give an example. You have a very big, you have a loaf of bread. Then that loaf of bread has slices. Then you are saying, in how many parts can you share that loaf? So each part, okay, as small, you are 20 of you, and you want to share a loaf of bread. Of course, that's not enough. So to make sure that everyone has a bite, you share it in very small, uh, uh, very small pieces. So those small pieces are what we are calling granules. Okay, and these granules are in two parts, which we'll talk about at a later stage. There is a fine granules and coarse granules. COARSE, coarse granules. We will talk about that at a later stage. So what we are basically saying is the DBMS or the users themselves, you can specify those small parts that you want to look up. So in databases, granularity refers to how detailed or fine grains of data is. So you are just talking about the details of that data. Okay, you break down. If this is the word, you look at how many times you can break it down, then how many times you can break it down until you can't break it down further. So it's just the detail there. So high granularity means very detailed. That's high. Low granularity means less details. Okay, that is low. Means low or summarized or aggregated data. SQLite provides database locking only. I'm told you guys are not using SQLite. You're using PostgreSQL. Is that true? Have you started the labs? Have we started the labs? Hello? Have we started the labs in this course? Okay. Good. Have we reached the locks? Have we reached the locks? Okay, good. So if you remember this, we did look at this. So you read A assigned to T, then you add 10 to T, then you write T by assigned back to A. And so on and so forth. And this is non-serializable schedule. Okay, compatibility is just a compatible. No wonder nowadays a clinic or a hospital is very important. Okay, you know, we grew up in a society where the two people love each other, they establish a home, then of course a wife gets pregnant, but she can't deliver, she miscarriages, she keeps on miscarriaging and the like. The problem that could have been prevented. So there are these issues of rhesus factors that we learn in biology. That's why the clinic or hospital is important. You go for testing. What are the chances of eliminating or that child being eliminated because of blood compatibility? Scanning for diseases so that you establish the trust in your partner. So what am I saying? You would find that because maybe you feel dependent on this guy, on this girl, and you mistaken that for love, then in a long run, she can't deliver. In a long run, you get to find out no, they are not okay. They are topping and the like. Then you begin panicking. You end up divorcing and so on and so forth. So what the point I'm trying to put across is compatibility. Okay, so you need to make sure that you go for a hospital test. The blood group, the diseases, and the like. You ensure that at the end of it all, the both of you are compatible to each other. Okay. In the same manner, in this we are talking about compatibility. Okay. So compatibility, in this manner, we are just saying will determine whether a transaction can acquire a lock on a resource. Okay, so we have these three compatibilities: IX, ISX, and IS. Okay, we will talk about these. So IX, okay, is compatible with IX. Don't worry, we'll talk about what IX is. Okay, and IS, but not with S or X. Don't worry, we will dive into that envelope. Okay, so SIX is compatible with IS, but not with IX, S or X. And I think I remember in the exam before us, there was a question on this. IS is compatible with IX, IS, S, but not with X. So what is the pattern there? I think this is where we'll start next time, which is Saturday. We have a makeup on Saturday. I believe we will start right here. Don't worry, we'll send you a question based on these. Yes, realizable and non-serializable. Unless you guys have a question, do we have a question? If you don't have a question, kindly give me a thumbs up. Kindly give me a thumbs up. Thank you for a clap. I appreciate that. Fafa, do you have a question? Okay, good. Previous, do you have a question? If we don't have a question, we're free to sign out. Have a good evening and see you on Saturday, 14 hours, God willing.